Okay, new chapter, new unit. We're now starting physical science. Remember, physical science is your physics and your chemistry, all the science that also includes the math. So for chapter 11, we're starting out with waves. We're going to talk about different types of waves, properties of waves, and then we're going to go into some specific types of waves. So for lesson 1, we're starting with what are transverse and longitudinal waves? First thing is, how do waves and energy connect? So first, a wave is just a vibration, any disturbance that causes a movement that transfers energy. Waves do not transfer matter from place to place, so it doesn't transfer the material. It may cause a material to move, but it only transfers the energy, and that can take the form of different types of energy. One of those main categories of waves are transverse waves. So, again, waves transfer energy. They may affect matter, but they do not transfer matter from one place to another. So, with transverse waves, the energy actually transfers forward, so like back and forth. The matter it affects moves in a perpendicular direction, meaning at a right angle. So the matter moves up and down while the energy moves back and forth. So imagine like a buoy floating on water. That buoy is just going to keep going up and down, even though the waves underneath it are going to be passing back and forth. Longitudinal waves have energy and matter that move in a parallel direction, meaning they move in the same direction. So it's easier to imagine a slinky when you're thinking about these. And it makes sense because that's kind of what longitudinal waves look like. So this image that's right here has a little tie attached to the slinky. So as you were to move this, the energy would move forward and backward, but also that little tie would start to move forward and backward as well. So it doesn't move in a perpendicular up and down direction like the transverse. It actually moves in the same direction. So this slide got cut off a little bit, but I'll tell you what it is. So different parts of a transverse wave, and you have a diagram of this in your textbook as well. But two of the main parts are the troughs and the crests. The crests are, think of like the peaks. The troughs are the dips. The resting position is, if you were to imagine the wave flattened out, that would be the position that it would fall into. Now, longitudinal waves don't have that same structure, so they don't have crests and troughs, but they have something that's kind of equivalent. A compression is the area where the regions kind of coil tightly together, and a rarefaction is that area where they are further apart. So now, knowing where the crests and troughs are for a transverse wave, you can measure the length of the wave. You can measure the length of the wave from any part that is the same. So you can measure it from crest to crest, you can measure it from trough to trough. For a longitudinal wave, it's the same idea. You just have to measure the wavelength from the nearest area that is the same. So you can measure from rarefaction to rarefaction or from compression to compression. So now we have the amplitude. So this is the distance from the resting point to either the trough or the crest. So think about this as like, how deep is the wave or how tall is the wave if it's a transverse wave. For a longitudinal wave, we measure the amplitude a little bit differently because, again, we don't have crests and troughs. We have compressions and refractions. So you measure them based on how tightly compacted those compressions are. So a higher amplitude is going to have very compressed compressions, and loosely compressed compressions will be a lower amplitude. So another thing about amplitude is it is related to the disturbance of the wave. So basically how strong that vibration or that disturbance that first created the wave, the stronger your amplitude is. So imagine that you have a rope in your hand, right? If you just wave your arm lightly, it's going to be a smaller wave than if you put a lot of force into making that wave. So now we're going to get into that section that has to do with math, but we need to define some terms first. So the first one is a period. So the period of a wave is the amount of time it takes for one entire wavelength to pass. So imagine that you had a marker, and remember you can measure wavelength from crest to crest, trough to trough, compression to compression. Once a total wave has passed, how long did that take? Frequency is a little different. Frequency is how many different waves pass a specific point in a certain time. And we typically use 1 second. We're measuring frequency of waves. So imagine you had like a marker and you took 1 second and measured how many different waves pass in 1 second. So the difference, a period, is how long does it take one wave to pass. Frequency is how many waves pass in a second. And we measure frequency in hertz. So there is a relationship between frequency and your wavelength. And I would draw these illustrations because tomorrow you're going to be doing a virtual lab that's going to require you to refer back to these things. So imagine again, you have that rope in your hand. The more force you put into it, or the faster that you wave it, that's going to have an effect on how short or how long your wavelengths are as well. So the shorter your wavelengths, the higher your frequency. If the waves are shorter, more of them can pass by that point in a second than if they are longer. So other ways that wavelength and frequency are related is that the speed of the wave also depends on the medium that it's traveling through. And a medium is basically the type of matter. So is that medium a solid? Is that medium a gas or a liquid? Is that medium pudding? Is it water? So whatever the matter is that it's traveling through depends on how fast it can travel. So for example, sound waves travel faster through liquids and solids than they do through gases. And I know that sounds like it doesn't make much sense to us, right? Because if we're yelling across the room and sound waves are traveling through air, we wouldn't imagine that those sound waves could actually travel faster if we're underwater. But that's true because the particles are actually closer together. And we'll get to that in a later chapter too. So that's something important to write down. So now the math, and it's not hard math at all. It's really just multiplication, but it's just knowing what to put where. So we have an equation for calculating the wave speed. So when you calculate the speed of a wave, the speed is going to equal the frequency times the wavelength. Now, one thing about math when we do it in science that we don't pay as much attention to when we do it in math class are units. So when you are looking at an equation like we have right now, they give you the units. You want to make sure that you're always using these units. So right now, you'll never have to convert units, but it will come to a point where they'll give you a wavelength in inches instead of meters, and you'll have to convert it to meters first. So we will get there, but I'm telling you that now to tell you that there's a reason that they put the units here because they are important. If you don't use the right units, you won't get the right answer. So the speed is always going to be meters per second, frequency is going to be hertz, and wavelength is going to be in meters. So here is a worked out problem for you. Let's look at that. So first, look on the left with me at the problem. We'll read it through before we start just looking at the answer. So the problem says, what is the speed of a sound wave that has a wavelength of 2.00 meters and a frequency of 170.5 hertz? And remember, our equation was speed equals your frequency times your wavelength. And I know we're probably like, why did we not just use S for speed or use W for wavelength? But that is because in physics we have a lot of words that start with the same letter, and so we end up using them for other things. S is usually seconds. Word can be something like W, and so we have this little symbol for wavelength that is called lambda. and we use v for velocity to represent speed. So now knowing that, we're going to just plug our numbers in. Our frequency they gave us in our problem, that was 170.5. Multiply that by our 2 meters. That is going to give us our answer of 341 meters per second. Make sure you remember your units because you will get half credit off if you do not put your unit. That is part of the answer, especially when doing math and science. So the last thing we'll talk about today are mechanical waves. Throughout this chapter, we're going to be touching on a couple different types of waves, but mechanical waves are basically the category of the waves we talked about today. So the matter is what's needed for these waves. Basically, mechanical waves need to travel through a medium. They need some sort of matter to travel through. Now, not all waves need a medium. Some waves, like light waves, electromagnetic waves, can actually travel through a vacuum like space, but mechanical waves need matter. So there are two types of mechanical waves. Those are transverse and our longitudinal that we've been talking about all this lesson. So there it is. That is lesson 11.1. Finish up your notes, and there are some videos on Classroom that I have there for you to take notes on as well.